Early multi-agent frameworks encountered a persistent failure mode, cascading hallucinations. When large language models are chained together naively, the output of one model becomes the prompt for the next. Small errors in the first step compound, leading to a complete breakdown of logic by the third or fourth iteration. It resembles the telephone game. When agents communicate using unconstrained natural language, information distorts with every sequential handoff. This compounding error is a structural flaw in the communication topology, not a reflection of the underlying model's intelligence. Human organizations solve this same problem of information distortion by moving away from free-form conversation towards specialized, documented handoffs. Incremental improvements in model scale will not fix the structural information loss. Solving the cascade requires a fundamental redesign of how these agents interact. MetaGPT addresses this by replacing open agent dialogue with standardized operating procedures, or SOPs. In this framework, the SOP functions as an assembly line. Role-play is replaced by a fixed sequence of narrow, sequential tasks. Coherence becomes a property of the architecture, ensuring the system stays on track regardless of the conversation's length. We will build this architecture layer by layer to see exactly how it cuts the hallucination cascade. Rigid bureaucracy provides the external structure necessary to pull multi-agent systems out of endless hallucination loops. The first layer consists of 5 specialized React-style roles: a product manager, an architect, a project manager, an engineer, and a QA engineer. When tasked with building a snake game, the system does not begin with code. The process initiates with business analysis from the product manager. The second layer mandates structured outputs as the only medium for communication. Each role produces a schema-validated document. The product manager outputs a requirements document with specific user stories, while the architect generates a system design detailing the file list and interface definitions. Unlike frameworks that simulate open chat rooms, MetaGPT roles do not talk to each other. Every exchange is a formal handoff. The schema forces the model to populate mandatory data fields, preventing it from passing incomplete or irrelevant context down the line. Because every handoff is a complete, unambiguous artifact, the cascade never receives the corrupted input it needs to begin. Once these documents are generated, they must move through the system without overwhelming the agents. MetaGPT uses a publish-subscribe bus. This global message pool is the single source of truth where every completed document is stored. Agents subscribe only to documents their role requires. The architect pulls the requirements document from the bus, but ignores QA logs. This collapses the communication topology from a complex web of crosstalk into an efficient, filtered bus. This bus enables a logic layer called dependency gating. There is no central scheduler directing the sequence of events. An agent remains dormant until the specific prerequisite schemas it needs appear on the bus. The global sequence emerges organically as these dependencies are met. This gating blocks partial or chatty inputs from propagating, ensuring the model only acts when it has a complete set of instructions. The engineer phase introduces a final check against the cascade by addressing a common flaw in LLM coding. Most systems rely on self-reflection, where a model reviews its code without running it. In software engineering, reasoning about code is not a substitute for execution. MetaGPT uses an executable feedback loop. The engineer agent generates unit tests and executes the code against them in a runtime environment. If the code fails, the agent cross-references requirements, system design, and its own execution history to debug and regenerate. To manage compute resources, this iterative loop is capped at a maximum of 3 retries. This execution loop alone accounts for a 5.4% absolute improvement on the MBPP benchmark. Errors are caught by the objective requirements of code execution rather than being evaluated by the model's own reasoning. The resulting metrics are significant: 85.9% on HumanEval and 87.7% on MBPP. However, evaluating these results requires looking past the top-line numbers. These benchmarks compare a multi-agent pipeline against single models, which mixes the quality of the architecture with the power of the baseline model. Furthermore, the token costs are not reported. Orchestrating 5 roles and a 3 retry feedback loop involves a considerable compute premium. Finally, the 3 retry cap is a resource backstop. It is not a mathematical proof that the code will eventually converge on a correct solution. These results validate the efficacy of the pipeline structure, but they do not suggest the underlying model has become inherently more capable. We must also recognize that these standard operating procedures are hand-designed by humans, not learned by the AI. The ceiling of the system is set by how effectively a developer defined the roles in their corresponding document schemas. MetaGPT occupies a specific pole in system design, standing in contrast to the highly flexible, conversational approach of frameworks like AutoGen. This is a deliberate trade-off, sacrificing conversational flexibility to gain architectural robustness. MetaGPT demonstrates that architectural structure provides a level of coherence that increasing model scale does not inherently solve.